Everyone to this last session of the day. So my name is Ani Majumdar from Princeton University, and I'm going to be chairing this session. So we're going to have a group of 5 talks and a Q&A session, and then another group of 4 talks, followed by another Q&A session. So the first talk in the session is called Mirror, Differentiable Deep Social Projection for Assistive Human-Robot Communication.
Hi, I'm Harold. Okay, there we go. So I'm going to present Mirror. This is joint work with my students, Kai-Chi and Jeffrey. Unfortunately, Kai-Chi couldn't be here today to present his work. So the problem we're trying to tackle is assistive human-robot communication. What is that? Essentially, let me explain with a simple example. So here we have a room with 2 agents, a robot and a human being. And the human, let's call him Jake, wants to get to the exit. All right. The wrinkle is that we've switched off the lights, so Jake can't see a box in the middle of the room. The robot can see the box because it has LiDAR, and we would like to enable the robot to figure out that it needs to tell Jake the box is there in order to, for Jake to safely make his way to the exit. Now, this is really challenging for robots because unlike human beings, they don't have a theory of mind. So we're going to adopt a planning-based method. The robot's going to forward simulate or imagine possible futures. And more often than not, it realizes that, if it does nothing, Jake is going to crash into the box. All right? So by tweaking its communication, it figures out eventually that it needs to tell Jake about the box so that Jake can safely make his way to the exit. All right, so that's at the conceptual level. Let's delve down into the technical details. So the way we are sampling these trajectories is by coupling a robot model and a human model. So the robot model captures the robot's beliefs about the world as well as its dynamics. So we are using a latent state space model that we train using a combination of variational inference and reinforcement learning. So from the robot's beliefs of the world, let's say ZT, we sample a particular observation, XT. We feed that to the human model, which captures Jake's behavior. That's going to spit out an action in a second. And then we're going to feed that to the forward dynamics, which will then give us the next state. And we can roll out this trajectory into the future. All right? So by changing these observations, XT here, we can provide communication in order to change the simulated human's behavior. Now, the next natural question is, what do you use for your human model? So you could, build one from scratch, handcraft one, using a cognitive model like SOAR or ACTAR, but this can be a bit labor-intensive. Alternatively, you could do what the cool kids are doing nowadays and learn a model, deep learning. But that also, you may run into issues because you might have our distribution problems because you're changing this axis here, right, in order to change the behavior for planning. So we are going to adopt a lazy kids approach, and we're going to copy over the robot model onto the human model. We're going to mirror that, okay? This is inspired by social projection theory, which is that human beings do this, okay? They use themselves, or the internal models of themselves when reasoning about other people, okay? So this kind of approach can work, but if you do it a little bit naively, it's not going to fly. And the reason for this is what Henny was talking about earlier, that robots and human beings are actually different, right? In this case, it's worse, because the robot actually thinks that Jake has LiDAR, which is just clearly insane. So we're going to have to counteract this via a little bit of learning, okay? We're going to leverage the structure in these state space models in order to put little learnable functions that we call implants. So we have perceptual implants. They are going to capture the differences in how Jake perceives the world relative to the robot, all right? We're also going to have policy implants, which capture how differently Jake behaves based on his beliefs, again, relative to the robot. And we think that modeling these differences is much more sample efficient compared to black box learning because you are leveraging the structure that's inherent in the robot model, for example, causal rules. Now, let me see. One last trick. Okay. Instead of modeling just single observation modalities, all right, you can model M different observation modalities, which will pop up in a second. Now, why might you want to do this? Because if you can think about these M different modalities as different communication channels. So now the robot can not only reason about what to communicate, but how best to communicate that information. So back to our example, the robot maybe doesn't need to tell Jake about the box. It can instead show Jake that the box is there. All right. So that's, I hope I managed to convey what Mirror is. My 5 minutes is almost up, so I'm just going to say Mirror works. Okay, we have a bunch of experiments showing that Mirror works on various domains with simulated agents, as well as with real-life human participants driving in order to avoid collisions, and with the agent providing useful information. All right. We are paper number 20, but poster number 16, all right? You can, if you don't manage to catch me at the poster, you can email me or email Kai-Chi. I'll be there to answer any questions you might have about the method, experiments, as well as, all the things that didn't work. Thank you very much, and I hope to see you at the poster.
So our next talk is called Robotic Telekinesis, and it's going to be presented by Arvind Sivakumar.
Hi, everyone. My name is Arvind, and I'll be presenting our work on robotic telekinesis. This is joint work with Kenny Shah and Professor Deepak Pathak. So robotic telekinesis is a low-cost vision-based system that allows any person to teleoperate a robot arm and hand just by moving their own arm and hand. So a single color camera captures a stream of video of the operator, and their motion is retargeted onto the robot in real time. So first, let's discuss some key aspects and requirements of our system. So firstly, we use only a single RGB camera with no depth sensors or calibration. And this means that in theory, our system could be used with any cell phone or tablet camera. Our system must work out of the box without any fine-tuning on every operator, regardless of their appearance or hand shape. It should work for any type of dexterous manipulation task. And it should work regardless of where the operator is located or what background they're standing against. So here we see an example of telekinesis being used for remote teleoperation via a video conferencing tool. But how do we train a system that can achieve these requirements? Like, where would we get the data that allows this level of generalization? So gathering paired human-robot poses for thousands of people, places, and tasks is totally intractable. But we do have access to an endless supply of diverse human hand manipulation videos thanks to websites like YouTube. And as we'll see, we train our system using only these human videos without any training or data collection on a robot. So first, let's look at our method. Our pipeline starts with a single color camera that captures images of the operator. We first estimate the pose of the operator's hand and body using powerful pose estimators that are themselves pre-trained on millions of images. We then retarget the human hand pose to a corresponding robot hand pose, and we retarget the human body pose to a corresponding robot arm pose. So first, let's talk about hand retargeting. So the key challenge here is that human and robot hands differ in size, shape, and joint structure, and we don't have paired human-robot ground truth correspondences. What we do have are millions of diverse human hand images that we can extract from YouTube, and we can estimate the hand poses using pose estimators. But still, we don't have the corresponding ground truth robot pose label, so how do we train a retargeter with only that data? So our solution is to take an energy minimization approach, and this energy function measures the dissimilarity between any human hand pose and any robot hand pose. So intuitively, if the human hand pose has the thumb and index finger close together like this, we'd want the robot to do the same. And the energy function formalizes this intuition, and importantly, it's differentiable. So we implement our hand pose retargeter as a neural network that will map a human hand pose to a robot hand pose. And this red curve represents this energy, or this loss, or this cost, being minimized over millions of everyday hand poses extracted from YouTube clips. And so in this way, we can train this retargeter using only human data and no robot data. And the resulting model is quite robust to variations in hand pose, shape, and size. So now let's talk about body retargeting. So this step is done analytically. And the key idea is that we care about how the operator's wrist is oriented relative to some anchor point like their torso. And so once we compute this relative offset, we can then use inverse kinematics to find a pose for the robot wrist with the same relative offset with respect to the robot's torso. Finally, we apply smoothing, interpolation, and clips to make sure everything is smooth and safe in real time. And putting it all together, our pipeline starts with a stream of video of the operator and produces a robot hand-arm trajectory that's executed in real time on the fly. So here we see it in action. Here we see 4 untrained operators that have never used the system before, completing a variety of manipulation tasks. And now let's discuss some of our experiments and results. So our first experiment tries to gauge how usable the system is for the novice operators like the ones you just saw. And the feedback from the subjects praised the usability and generalizability of our system, but also did highlight a few failure modes and retargeting that we hope to address in future work. Our second set of experiments aims to study the trade-off between using this neural network for retargeting versus using online gradient descent at runtime. And we find that the speed and robustness of our network to be very beneficial, but we do note that because our network learns such a strong prior over everyday hand poses, like the one seen in YouTube clips, it can suffer on complex, rare, out-of-distribution hand poses. We have several other experiments and ablations that I won't go into detail here, but we invite you all to check out our paper, poster, and website. Thank you for listening.
So our next talk is underwater robot-to-human communication via motion.
Okay, good afternoon, everyone. My name is Michael Fulton. I'm pleased to present this work along with my colleagues from the Interactive Robotics and Vision Lab at the University of Minnesota Twin Cities, if the video comes up. And this is actually a great connection with Henny's talk because this is nonverbal communication with not very much human similarity. So we're working in the context of underwater human-robot interaction here. Underwater HRI is a field which has developed pretty quickly over the last 15 years or so, with the emergence of human-portable, human-scale, autonomous underwater vehicles. The core focus is enabling collaborative work between humans and AUVs using communication between the two. Now, when we look at communication in the underwater environment, when the AUV is communicating to the human, it's mostly through text displayed on integrated digital displays. Now, this is great because you get high-density information displayed very succinctly. However, digital displays are extremely hard to read underwater. You can see in the video here the diver pulling the robot close to his face so that he can read it. If it's far away or rotated at all, it's almost impossible to read. So we were interested in exploring more natural, human-like communication systems that could be used at a variety of different distances and orientations. And that's where robot communication via motion comes in. So we proposed this back in 2019. We proposed RCVM, which is this method of using full-body robotic motion as a stand-in for human gestures. We call these kinemes, motion with semantic meaning. And we discovered in 2019 that in our simulation-based RCVM, it outperformed a light-based communication baseline system. Now, that's all well and good. However, what happens when we bring things to the real world? Real-world motion control in the underwater space is much more difficult. So how is RCVM going to perform when we implement it, as we've done in this paper, bring it to the real world, and compare it to alternative types of communication? You can see here the follow me kineme being demonstrated on the Aqua AUV, telling the diver to follow the robot. Now, when I say baseline types of communication, other alternatives, I'm talking about light-based communication with an array of LEDs, integrated digital displays, as I mentioned, which are the primary method used, and then also audio-based text-to-speech communication. We used the Google Text-to-Speech API to generate phrases and play them over a waterproof speaker. See how that worked out. So this paper, we present two studies on this. The first study was an in-person pilot study where we integrated RCVM into the context of a full interaction loop. So we trained people on what the kinemes of RCVM mean. Then we had them ask the robot a question with a gesture, receive an answer via kineme, and then take an action. Based on the actions that participants take, we can then infer which kineme they recognized, and we see, while there is a perceptible drop in accuracy from our simulated version, we still get a pretty good overall kineme recognition. Now, this is excellent, but how is it going to compare to these other baseline communication methods that I talked about? And in particular, what happens when we look at RCVM at different distances and at different orientations? And that's where our multidimensional study comes in. This is an online study due to the scope of the problem, so we recruited people on Amazon Mechanical Turk, trained them in the use of one of these 4 communication systems at an ideal communication viewpoint, and then we asked them to identify phrases from that system at a different viewpoint. So 3 meters distance, 8 meters distance, 45 degrees, 90 degrees rotation from the camera. And this is a much more challenging issue, much more difficult. Now, the main thing that we see here is that while RCVM does not outperform any of these systems at the ideal viewpoint, it is much, much more resistant to viewpoint change. The LCD and text-to-speech communication systems drop off almost immediately as soon as you take them away from their ideal viewpoint, whereas RCVM, and to a lesser extent the LED communication system, are much more resistant to change. And we can see that in the graph here, both in terms of the raw accuracy, did people recognize the phrase correctly, and in terms of what we call operational accuracy. How correct were people when they were confident that they were right? So we see RCVM does not perform the best at the ideal viewpoints. However, when you look at these challenging viewpoints where these typical methods of communication just fail, RCVM can help us fill in the gap there and make this much, much more robust. So in this paper, we've presented our implementation of RCVM for real robots and 2 studies establishing where RCVM fits in the general scope of underwater robot-to-human communication. Generally, we see that RCVM is recognized decently well and is much more resistant to viewpoint change than other types of communication. I'd like to say thank you to all my collaborators, funding partners, and everything else. Come see us at the poster session. We're poster 18. Thanks.
So the next talk is called Gaze Complements Control Input for goal prediction during assisted teleoperation, and it's going to be presented by Ruben Aronson.
All right. Hello, everyone. So I'm Ruben, and we're jumping right into it. All right. So teleoperation is a really important control modality for a lot of important tasks. However, it's hard for people to control robots, especially for manipulation actions in high degree of freedom situations. One strategy to resolve that problem is shared control, in which the system predicts the user's goal from some of their perceived behavior and then autonomously plans a robot action to achieve that goal. We're going to be looking at that goal prediction step, and in particular we consider 2 sources of goal information. First, the user's control input, which we will actually show is probabilistically optimal when the system is simple, but doesn't give sufficient information in more general cases. And next, we'll be looking at the user's natural gaze behavior, so where they look during the task. And we'll show that it provides complementary information about the user's goal, but it gives less reliable information. And together, they can give you a better picture than either alone. So why control input? Control input is a common startup modality, mostly because it's already available to the system, right? So the user is providing a joystick input, and you already can use it. We can actually, so to understand it better, we can work through an example. So here's a sort of example scenario in 2D. So you can imagine you have a robot at A moving towards one of the 2 goals indicated as green stars. And we'll look at the optimal robot action and the user's likely control input at a couple different points of the task. And so at the beginning, we see that both actions are towards the right, which is independent of their goal information. And so the system doesn't need any goal information to make that action. In contrast, at point C, the action requires goal information to proceed, but the user gives that goal information because it's the optimal way to make progress. And we actually show that when the user is noisily optimizing the same MDP as the robot, that accounts for most of the situations. And so we can actually have guarantees on the user's behavior. However, this doesn't necessarily extend to more general problems. In particular, when the user's input is restricted, such as during modal control, we don't have these guarantees anymore. And so to look at an example of that, we can consider a separate point. So here, imagine that the user can only provide input along the axes, whereas the robot can move in any direction in 2D. We can see at point B over there that the robot would be able to benefit from goal-directed motion, from goal information to give optimal motion, but the user information doesn't give enough information. In contrast, so the point we look at user's natural gaze, and to compare the relative usefulness of each of the input signals, we ran a user study. In this study, participants teleoperated a robot using shared control-based assistance, and we used to predict their goals either their control input, their eye gaze behavior, or both of them combined. To design the task, we designed a task that sort of mirrored our 2D example, in which the goal optimal location differed in both X and Y, and users were restricted by the joystick, by the control of the robot, to only provide motion in 2 axes at a time. And we find that when the system gets early information from gaze, it improves on the task metrics because it allows for assistance in the directions of motion that require goal information to proceed, because the control input has not yet given it. However, when we combine everything together, we see that gaze does not actually improve over control input alone in aggregate, largely because gaze itself is not a particularly reliable signal, and that we both don't see particularly many glances towards the goal. And when people looked at the goal, as Hani and Moni said earlier, it can perform a pathological behavior because of a failure to recognize the states. Here we can look at 2 different signals for goal prediction, and by understanding their relative roles in the task, we can build a system that works better together. Thank you.
So our last talk in this block is called A Negative Result for Learning from Demonstration, Challenges for End Users Teaching Robots with Task and Motion Planning Abstractions.
Good afternoon, everyone. I am Nakul Gopal, and here to present our work on negative result for learning from demonstrations, challenges in end users teaching robots with task and motion planning abstractions. So the domain that so our foremost motivation is we want people to be helped by robots. So Georgia Tech has an AI for Caring Institute where we see how elderly people could be helped with robots. But there's a problem whenever we need to teach novel tasks to robots. For example, cooking. So here's Julia Child's recipe for scrambled eggs. It comes with like 6 variations. How do we teach these tasks to a robot with like a few demonstrations? So what's nice about these tasks is that they're long horizon. They are multimodal. They involve contact with different objects like eggs and spatulas, and you can easily specify multitask specifications on them. In robotics specifically, there is the formalism of task and motion planning that allows us to specify and solve these problems. So what we want to do is we want to see if people can teach robots with task and motion planning abstractions. In related work in robotics, people have already looked at teaching robots using keyframe specifications or hierarchical task networks. In reinforcement learning, there's the options framework, and in CogSci, we have already studied how people learn and teach using abstractions. But what we want to do is we want to see if robots specifically can be taught by people using task and motion planning abstractions, and what kind of inducements can we give them so that they teach with task and motion planning abstractions. So our first research question is, do people naturally teach with abstractions? And our second research question is, what type of inducements or external factors can be given so people start using abstractions when teaching robots? And finally, we see what kind of explicit instructions will help people use task and motion planning abstractions when teaching tasks to robots. So our domain is a soil mixture domain where we've got sand, lime, and manure, and the users teach the robot to create multiple ratios of these objects. So the users give kinesthetic demonstrations for subtasks that then they can chain to solve larger problems in this interface. And they don't need to use abstractions at all. They can directly just give an end-to-end demonstration. So the type of demonstrations that users can give are end-to-end demonstrations where they do not use any abstractions at all, or they could use some sort of object-based abstractions when teaching the robot, which don't have any preconditions or contact specifications. And finally, what we care about are tap-based abstractions that have the highest amount of generalizability. So we created an abstraction score that actually grades these levels of abstractions that users provide to robots. To study this problem, we conducted 2 user studies. And in the first experiment, we provided users with a baseline condition which just had a single task setup, which was followed by a multitask setup and a phase with a lot of internal repetitions to see if people use abstractions when teaching robots in those 2 conditions. And finally, we just gave them written instructions to teach TAMP-based subtasks to the robot. We noticed that people did not do well in teaching TAMP-based abstractions over there, so we conducted a second experiment where after the baseline condition, we had an analog video of an analog task like block stacking, and we showed them a debug demonstration of the task that they were teaching the robot, followed by an expert video task. So to our results, people do not use abstractions when teaching robots. So the majority of the participants just didn't. And external factors like repetition or multitask setups perform equally well as the baseline condition when teaching the robot. And finally, only the expert video helps consistently in helping people teach the robot tasks with TAMP and motion planning abstractions. But the problem here is that experts are not always available. So we took the demonstrations that users gave us, and we actually taught the robot tasks using the demonstrations that they gave. And if the task has already been demonstrated to the robot previously, the robot can solve the tasks irrespective of the quality of abstraction. Moderate quality abstractions, which are object-focused, can solve novel configurations that were unseen. But only TAMP-based abstractions can generalize from novel locations on the table because TAMP-based abstractions take into account contact specifications and preconditions when solving the task. So our key takeaways are that participants do not naturally use abstractions when teaching tasks to robots. And the instruction medium that helps them most is an expert video teaching the tasks to robots, but experts are not always available to teach tasks to robots. So it creates this problem. Thanks a lot.
So we now have a Q&A session for these papers. So I'd like to invite the authors to come up. Are there questions in the room? Go ahead.
Yeah, I have a question for the underwater communication paper. Great talk. So I'm just wondering how are the how do you say kineme designed?
Oh, how are the kinemes designed?
Yes.
Yeah. So it's an iterative process where we start by looking at our list of things that we want to communicate. Then we check and see if there are direct human analogs, like for instance, yes and no, nodding and shaking the head. If there are direct human analogs that we can mimic, we go with those. If not, we look at the concepts involved in the phrase that we want to communicate and try to structure something off of that. This is something that we have a lot of open work in because it's a very difficult task, and right now it's very handcrafted, but we're hoping to provide a little more analysis on that in the future.
Thank you.
My question is actually also for the underwater talk. I'm very curious about what you see with the bandwidth difference between the LED signals, the kinemes, and the LCD screen, which is obviously going to be able to communicate more information. Do you feel like you're limited in what you can communicate and what's needed for the tasks you can do by that bandwidth? So the bandwidth difference. Yeah, so when the information is very specific, it's hard to communicate it, very specific and not directional. I would say it's hard to communicate it with motion and with LEDs, at least the LED systems we've had so far. We have new LED systems under work that are more highly dimensional and can communicate more information. It's definitely LCD system, text-to-speech system when it works. LED and RCBM on about the same level in terms of dimension or in bandwidth, but personally I think motion works better than lights, and we've seen that so far in our work in general. Thank you, really interesting work.
Thanks.
Dave, go ahead.
Hi, I had a question about robotic telekinesis. You mentioned that the neural network performs less well on out-of-distribution poses, but it's faster than energy-based optimization. Have you tried using neural network to initialize the energy-based optimization to try to get the best of both worlds?
Yeah, I think that's a great idea, and I think there are a lot of in-betweens between these two extremes of neural network and energy-based optimizations. So the one you suggested would, I think, be very promising because A lot of the issues with using online gradient descent are issues of seeding and initialization. For example, if the solver fails at one iteration, the next iteration would be seeded from the failed solution of the previous iteration. So I think something like that would be very powerful to get the speed of a neural network with the guarantees, if you will, of gradient descent.
Cool, thanks.
I have a question for the mirror paper. So I'm just wondering, what is the model reconciliation process you're using? I'm assuming from how the language has been generated once you recognize the human is about to make some mistake or something like that.
So I think the question is about how we generate the language in the setup. So we actually use a similar to autoencoder-like model with a pre-trained GPT-2 model within. So that's how the text is being generated to the person, and then we use a text-to-speech sort of module to just output that in terms of audio.
Cool.
Yep.
Thank you.
So I have a question also for the robotic telekinesis work. So you mentioned that you do some kind of pre-training based on YouTube videos, and I'm wondering if you see a bias in that data set towards right-handedness, and if you do some kind of data set balancing to also generalize to potentially left-handed users.
Yeah, so we do see bias. The way we handle this particular bias is we don't train on left-handed clips. So right now, one limitation of our system is that it only works for right human hands and right robot hands. So this is definitely something that we hope to address in the future. I would say other types of bias that we see when you use training on everyday tasks like those you see on YouTube are somewhat of a bias towards what you might call common hand poses that are used in everyday interactions. Whereas if faced with some very obscure hand pose like this, our network may struggle just because it's out of the distribution of training data.
Thank you. Maybe we have time for one last question. Go ahead.
Okay. I have a question for Ruben. You mentioned that you're using both the gaze and the joysticker. Did you consider these two different control or human signals had different delay?
Sorry, can you repeat the last part of the question?
Did you consider the joysticker inputs and the eye gaze have different delays? They probably do not match each other on they probably not happen at the same time.
Yeah, so I'd say loosely the big advantage of gaze is that it could occur, or it tended to give you earlier information than the control input did. And that was sort of because of the process of the task, where there was sort of this I didn't get into it in the talk, but the task sort of has two phases where there's a general motion that was sort of common for both goals, and then there was individual motion for the specific goal that they were doing, and people tended to do the common motion for both goals first, and then do the individual motion. And so their user input didn't give goal informative information until after they'd switched to the goal-specific mode. But the gaze could give it earlier. One of the interesting things we did find, though, is that as people sort of learned to use the system, they kind of understood and they started deliberately giving goal informative information earlier with the control input, just to sort of, so the dynamics are very much more sort of how people happen to control it rather than something that we would expect to be sort of reliable or guaranteed.
Thank you, great talk.
All right, I think we're going to move on to the last block of talks. So let's thank our speakers again.
Yeah, right, we'll have time.
So the next talk is going to be human motion control of quadrupedal robots using deep reinforcement learning.
Thank you for the introduction. I'm Sonu Kim. Autonomous robots can enter dangerous environments, such as disaster recovery scenes, instead of human workers. However, they often fail in unforeseen scenarios since they are overfitted for the training process. This limitation motivates us to develop a flexible motion control interface agnostic to testing time missions. Here's the illustration of the proposed human motion control interface. First, the user aims to hit the ball. Notice that the ball is located higher than the standing height, so the user tilts his body while manipulating his arm. The hanging bone is even higher than the ball, so the user controls the robot to sit to reach the target. Moreover, the user can perform reactive controls such as touching a flying ball. In our system, the main challenge comes from the morphological difference between the human and the robot. We should find the robot motion that reflects the user's intention and is also physically plausible. Our system consists of three main components. First, the retargeting module maps the capture human motion into the robot's kinematic space. Then the control policy learns to track the retargeted motion in the physics-based simulation. Finally, we apply domain randomization for better real-world deployment. First, I'll explain the retargeting module. Previously, we often tackle motion retargeting using feature-based approaches that optimize poses depending on predefined rules. However, they require complicated calculation, which is not suitable for the real-time application. On the other hand, the data-driven approaches are less costly at execution and is also providing additional flexibility. We take the idea of supervised learning to build our data-driven retargeting module. Our neural network acts as the retargeting function, providing agility and the flexibility. The loss function is designed to minimize the difference between orientation, joint angles, and the end effectors. However, the learned function often generates the physically invalid motions, leading to control failure. To handle this issue, we correct the consistency as post-processing. We first correct the contact consistency by predicting contact flag and fixing unnecessary fuscating. We also suppress the temporal consistency to prevent abrupt joint movements. As we can see here, both corrections are essential to maintain physical validity. We further construct motion hierarchy to allow users to execute various motor tasks seamlessly. The motion selector chooses the motion state depending on the proximity of current human to the training data. Then the next task is to track the retargeting motion in the physics-based simulation. We train the motion imitation policy using deep reinforcement learning. The reward is designed to minimize the difference between reference motion and the simulated motion. We introduce curriculum learning to obtain better performance. We introduce our curriculums on both task difficulties and types, from a narrow range to the wider workspaces for the difficulties curriculum, and from a single task to a combined task for a types curriculum. Without both curriculums, the policy generates the conservative behaviors. Finally, we apply domain randomization for sim-to-real transfer. We randomize the simulator parameters such as mass, PD gains, or friction coefficients during the training. Without domain randomization, the hardware fails without domain randomization. We can perform various tasks using our system. As we can see in this video, the user can push the tennis ball and the dominoes. In this mission, we aim to push the box to the target location. Initially, the box is too far from the robot and not reachable. So the user controls the robot to walk and push the box repeatedly to locate it on the target position. Thank you for listening, and please visit our website and the poster session.
So our next talk is rapid locomotion via reinforcement learning.
Hi, so I'm Gabe Margolis, and I'll be presenting our work on rapid locomotion via reinforcement learning, a robust and scalable approach to legged robotic sprinting. So recent work has yielded dramatic improvements in robotic walking in the wild. This line of work predominantly uses reinforcement learning coupled with domain randomization to yield policies that are highly robust to disturbances. Other work has demonstrated running at high speeds. High-speed running controllers developed in the past few years have mostly been handcrafted rather than learning-based. However, neither have matched what we've seen in nature, that is, animals that are capable of achieving high speed on natural terrains. We ask what solutions can scale to solve this combined problem. Locomotion in the wild is hard due to dynamic variations that are not present in a laboratory. The robot's feet may sink or slip into the ground. Geometric variation in the terrain also impacts the robot's motion. Fast locomotion imposes a complementary set of dynamic considerations that are not present at low speeds. These include operation at actuator limits, the regulation of high contact forces, and body control during flight phases. These factors compound the system complexity. So, how does existing work address locomotion in dynamically complex settings? One approach is to implement targeted improvements to hand-designed models used in analytical controllers. Existing approaches can compensate for terrain compliance, flight phases at high speed, or terrain geometry. However, integrating these systems while adhering to a computational budget is a challenging engineering task. A promising alternative is to use reinforcement learning. Rather than relying on a human to design a computationally efficient model for a complex phenomenon, we can attempt to directly optimize a policy through interaction with the simulator. In this work, we take lessons learned from in-the-wild locomotion and apply them to high-speed running. The inputs to our neural network policy are raw sensor readings, past actions, and the desired linear and angular velocity of the body, or the command. The policy operates in an action space of joint angles. This keeps our system simple to deploy and avoids any unnecessary constraints on its motion. So, what's hard about using reinforcement learning to run and spin at high speed? Let's consider this plane where the x-axis corresponds to sprinting speed and the y-axis corresponds to spinning speed. A slow walking controller performs well when trained on the narrow range of commands shown here. To achieve high speed, one must train on a larger range of commands. However, if you try this, the agent no longer learns to walk at all. Why does the agent fail? From the start of training, it is being assigned high-speed tasks, which are very hard. This yields little reward and hinders learning. One way to address this is to gradually increase the difficulty of tasks, an idea well known as curriculum learning. Instead of manually designing the curriculum, we develop a strategy that automatically increases the command complexity. This scalable approach enables the acquisition of walking and running behaviors. While this works, there remains a problem. Linear and angular velocity are coupled. One can either run fast or spin fast, but centrifugal force prevents their combination. This causes many high-speed commands to be physically infeasible. If we do not admit conditional dependence between linear and angular velocity, the agent is exposed to an increasing rate of infeasible commands as its speed climbs, which leads to many poor-performing episodes and hinders learning. To address this, we applied a curriculum strategy that automatically accounts for the dependent coupling between variables. This enables stronger performance for high-speed running and spinning motions. What is feasible is also dependent on robot properties such as mass and terrain properties such as friction. Identifying these properties online using a learned module further improves agility, and more so when running at high speeds. I'll conclude with some videos. This video shows a max speed test of our end-to-end learned controller. It sustained a top speed of 3.9 meters per second, slightly faster than the previous record held by a handcrafted controller for this robot. The same controller can also spin at speeds comparable to the fastest handcrafted controller. The benefit of reinforcement learning really shows when the robot is taken outside of the lab. Here it spins on an icy patch as its feet constantly slip. It averages 3.4 meters per second for a 10-meter dash across uneven grassy terrain. A baseline MPC controller fails on this challenging gravelly hill that is both sloped and granular. Our controller moves in an unintuitive way, but makes it up the hill. And does a little spin at the top. So we'll be showing a live demo of our controller at the Contact Workshop on Friday. Thanks for listening.
So our next talk is called Human to Robot Imitation in the Wild.
Hey everyone, my name is Shikhar, and I'll be talking about human-to-robot imitation in the wild. This is joint work with Abhinav Gupta and Deepak Pathak at CMU. Consider these cooking videos. Can we teach robots the same skills from watching humans? We aim to answer this question in our paper. Our work consists of directly learning from human videos in the real world without training and simulation. The key idea is to extract priors from these videos and then improve and explore around these in the real world. Our work scales up to many different tasks in the wild. In fact, we performed 20 different day-to-day tasks that we found all around campus, as you can see here. Now let me walk you through how this approach actually works. Firstly, the robot watches videos of humans performing different tasks, like opening a fridge. From these, we can extract information about hand-object interactions, as well as hand motion. We call these our human behavior priors. Using simple 3D computer vision techniques, we define a mapping function to the robot's end effectors, and then we execute this in the real world. Now, you see that the robot gets close to opening the fridge, but it does fail. So it needs some practice in the real world. This is the repeat stage of our method. But given all of this repetition, how does the robot actually improve? In order to improve, the robot needs the human video to guide this. But consider these drawer opening videos. We can't really compare them well in feature or pixel space because there's a large embodiment gap. However, if we mask and in-paint the agents out of the video, we can actually do so. Thus, we build an agent-agnostic cost function using human and robot in-painting videos. We use this agent-agnostic cost function to improve the policy in the real world in an efficient manner. In fact, our policy consists of two different submodules. Firstly, a task policy aims to minimize the agent-agnostic distance between human and robot videos. But in order to not be too close to the prior, we encourage the robot to try new things using an exploration policy. The goal of this exploration policy is to maximize the agent-agnostic change. More concretely, this is the visual change in the agent-agnostic embedding space. We call our approach WHIRL, or in the wild, human imitating robot learning. To summarize, we first compute 3D human priors, we project these to the robot's action space and execute them in the real world. We use a change-based objective to perform exploration, and then we improve our policy using our agent-agnostic cost function as well as our exploration metric. Now, let me show you an example of WHIRL in action. On the right, we have a human video as input, and on the left, we show a time-lapse of the training procedure for our method. Using our sampling-based optimization strategy, within about 60 episodes or 1 to 2 hours of training, WHIRL learned to solve the task pretty well. In fact, even within a couple of iterations, we see a drastic improvement in performance. We use the same sampling-based optimization strategy to optimize both the task and the exploration policies. Now, let's look at some results of WHIRL applied to many different settings. As I mentioned earlier, we performed 20 different manipulation tasks in the wild. Videos of all of these are available on our website, and here I've shown you a subset of these. For each of these, the robot only gets a single video of the human performing the task, and then we run WHIRL for about 2 hours. Note that the camera angle between the human and the robot video don't have to be the same, as well as the starting position of the robot doesn't have to be the same as that of the human. We performed thorough comparisons between WHIRL and many different state-of-the-art baselines, and we find that all of the components of our method, like the iterative improvement, the agent-agnostic cost function, as well as the exploration policy, are very important. On the plots on the left, we see that success definitely improves with more interactions in the real world. Thanks for watching this presentation. For more information, we encourage you to visit our website and our poster. I think it's number 23. Thanks, everyone.
So our last talk for the session is called Variation Inference MPC using Normalizing Flows and Out-of-Distribution Projection.
Okay, thanks. Hi, I'm Thomas. I'll be discussing our work in which we propose learning sampling distributions for MPC using normalizing flows. The learned sampling distribution generates goal-directed and environment-aware controls, and we additionally propose a method for adapting the learned sampling distribution to novel environments. So first, let's give a little bit of an overview for sample-based MPC. So consider the following navigation problem. We frame this as finding a control sequence that minimizes the expected cost. So popular sample-based MPC methods iteratively update a control sequence using Gaussian perturbations. And this process is really as good as the samples. So if we add in obstacles, and now all these samples are high cost, when iteratively resampling, we can become stuck in a local minima. In contrast, samples from our proposed sampling distribution are shown on the right here, and they show qualitatively different trajectories that reach the goal while avoiding obstacles. So how should we train this sampling distribution? Well, intuitively, we want a sampling distribution where the likelihood is related to the cost while maintaining diversity. We formalize this as Bayesian MPC, first introducing a binary optimality variable. The goal is then to find posterior over low-cost control sequences. We use variational inference to approximate this posterior, minimizing the KL divergence between our approximation and the true distribution. This results in the following objective, where we're essentially minimizing cost of the samples while also maximizing the entropy. So now I'll go through the whole proposed sampling approach. So the inputs are at start, goal, and the environment. We use a VAE to encode the environment to a latent representation H. We use a normalizing flow as the lane space prior, which is learned during training. We encode H, the start and goal, into a context vector. And then the control sequence normalizing flow takes the context vector and transforms normally distributed samples into low-cost controls. Our total objective combines the expected cost of controls, the sampling distribution entropy, and the VAE loss. The space of environments is very high-dimensional, and we couldn't cover it with training data, so we would like to adapt to novel environments. And to do this, we use the VAE. So looking at the VAE loss, we see that there's this prior likelihood term, and we can use this as an out-of-distribution score. And we found that using the normalizing flow prior made this score very effective. However, we don't want to project arbitrarily towards the training distribution. We'd like to encode relevant features of the environment. So we encode the environment to H. We then evaluate the OOD score for H. We then use H to generate trajectories. And unsurprisingly, a lot of them are in collision. To do the projection, we combine the OOD score with the cost on the resulting control distribution, and this results in a new environment representation that we can use for sampling. Iteratively running this projection online, it effectively hallucinates an environment close to the training distribution, which also results in low-cost trajectories. We incorporate our flow into MPPI, a widely used sample-based MPC method. MPPI iteratively updates the control sequence using cost-weighted sum of Gaussian perturbations. We can instead generate samples using our flow model. We actually use a combination of both, generating half using the flow model and half using Gaussian perturbations. We demonstrate our approach on a planar navigation task with double integrator dynamics and a quadrator task, 12 degree of freedom under actuated. And we evaluate on complex novel environments in both cases. We additionally evaluate on real-world environments for the quadrator task generated from real-world data. Our approach shows improved cost and performance over baselines across different environments, novel environments for both the planar navigation and the quadrator, as well as improved performance on real-world environments for the quadrator. The OOD projection effectively hallucinates obstacles in order to steer the trajectory away from potential collisions while ignoring features of the environment that are not relevant for the current navigation task. We've since extended our approach, incorporating it with another sample-based MPC method, improved CEM, and performed an additional experiment using a 7 degree of freedom arm, including with a real robot in the lab. Overall, we present a method for learning a sampling distribution for MPC, which generates goal-directed and environment-aware controls. We additionally propose a method for adapting it to novel environments. And we've shown that we can perform this adaptation to kind of complex real-world environments, even when we're training on like very simple artificially generated environments. So thank you, and I invite you to come and talk to me at the poster.
All right, I think we have a few minutes for questions. Go ahead.
Yeah, hi. I have a question for the last talk. I would think that there might be a trade-off between generating smart flow-based samples, which might be a little bit slower, versus generating many dumb samples from like a Gaussian prior. How do you think about that?
That is true in general, but like what we found was that yes, using the flow takes longer than sampling from a naive Gaussian, but you have to evaluate them. You have to compute their cost, and it turns out that like rolling out your dynamics and evaluating the cost of trajectories actually is an order of magnitude more expensive. So the difference is kind of negligible. We found really the main cost is in evaluating the controls.
Great answer. Thanks.
Let's take a question from the other side.
I have a question for the rapid locomotion talk for Gabe. I'm curious, how do you label a control input as feasible versus infeasible? Do you require like a prior label of which pairs are feasible and of that like boundary of feasible inputs, or is that boundary learned?
Yeah, great question. So right at the start of training, we don't know what the boundary is, and we don't manually derive that from the physical constraints. We're just sort of growing the distribution of goals by adding goals as nearby goals achieve high reward during training. And it naturally sort of converges to agree with this physical feasibility boundary. Yeah.
Okay, thank you.
Go ahead.
Cool. I have a question for author of Whirl. I wonder how is a reset of the environment handled during robot exploration phase? And also, how can we change the system to make it, for example, robust against viewpoint changes?
Oh, great question. So for reset, for now, a human has to do it, but this is part of future work that we're working on, how to autonomously select goals so that we can go out and the robot can practice, so that it doesn't need to reset. So for example, you can imagine watching somebody for multiple hours in their kitchen, and then you try to go and you can sample like many videos, so you don't have to try to sample the same video of the same drawer being opened. And then for handling multiple viewpoints, I think there are you can either try to train a model that can handle multiple viewpoints, so your policy could try to be trained on multiple robot viewpoints, or we can try to use more robust off-the-shelf computer vision models as well.
Thank you.
I think we can take one final question.
Yeah, I have a question for the Whirl paper too. So it's similar to the generalizing to different viewpoints, but beyond viewpoints, does your method kind of generalize to different novel objects, like opening a different cabinet or different drawer, beyond the training demonstrations?
Yeah, that's a great question. So if summarizing your question is, how would we handle generalization to new objects, et cetera?
Yeah, or new instances.
So we actually have an experiment that generalizes to, for example, a similar looking but different dishwasher or different drawer or door. It still looks approximately similar, so that's why it's easier to match the visual features. I think, again, training maybe with more examples instead of training on a single kitchen, maybe on hundreds of kitchens. That might help solve it.
Okay, cool. Thanks.
All right, I think that concludes this session. Let's thank our speakers again. And I'll hand it over to Matteo for some final announcements.